so let's talk about chemical reactions, and today we're just going to be doing a very high-level introduction to them. So let's get started. So the first thing is we have to discuss what is a chemical reaction, what happens in a chemical reaction, how might we know that a chemical reaction occurred. So a chemical reaction, it's the process of one or more substances being rearranged to form a different substance. This is known as a chemical change. It's important to note that when you add two elements together to make a compound, that's a mini chemical reaction. You can represent it as a chemical reaction. But for the chemical reactions that we're really going to be looking at, you're going to be taking compounds and rearranging them to make new compounds. And there's a large variety of ways that you can tell if a chemical reaction has taken place. There can be a temperature change. When a reaction absorbs heat and gets cold, that's considered endothermic. When a reaction releases heat and gets hot, that is exothermic. There can be a color change. It can be very obvious color change. It might be a slight color change, but there's a color change. There might be a precipitate. This is normally a solid that will fall out of the reaction. You think of a precipitate from the word precipitation. Precipitation falls from the sky. A precipitate falls from a reaction. Most precipitates are solids, but you can also get liquids and gases as also a form of precipitate. You might smell the reaction. You might get a sulfur smell or different types of smells that were not there before that'll show you that a reaction occurred. Sometimes you get bubbles that show, and sometimes reactions are so subtle they're really hard to detect, and that's why we can read the reaction in chemical formula form. Okay, so now let's look at some examples of chemical reactions. Right here, you can see it was clear turning yellow. This might be a color change. This one here, you can see the like exploding out the top. It's supposed to be a release of heat. This one here, you can see the color gradient. It is a color change. If this green on the bottom was a solid, it might be considered a precipitate. This one's a little trickier. It might be a release of gas, depending on the reaction. You see the vapor there. You can see bubbles here. It might be bubbles or it might be hot. You can see the red. If that red wasn't there before, it might be a color change. This one here, you can see the white on the bottom. That's often a precipitate. You can see the different colors. That's a color change. And you can see the fireworks, meaning this one was supposed to have been a release of heat. And this one over here, you can see all the different colors that occurred. This is a color change. So the cool thing about this is that some reactions might have more than one way of telling that a reaction occurred. So when we're looking at representing chemical reactions, your reactants are your starting substances, and these are on the left-hand side of the equation. Your products, which are your ending substances, are on the right-hand side of the equation. Please note that unlike in mathematics, your reactants will never equal your products. We don't use an equal sign. We use directional arrows. So reactant 1 plus reactant 2, then you have a directional arrow, which means produces, creates, goes to product 1 plus product 2. Reactants create or produce products. They're not equal to products. Okay, so let's look at how we might actually write a reaction, because here's the deal. You don't just write reactant 1 plus reactant 2 produces, creates directional arrow to product 1 plus product 2. You have to make sure that you're including the state and proper format next to your reactants and products, because the state gives us a lot of information that is necessary. Is it a solid? Is it liquid? Is it gas? Those states kind of tell you what might be happening. So here's how the states are denoted. And these are all lowercase. So an S in parentheses means solid. An L in parentheses means liquid, and again, all lowercase. A G in parentheses means gas, and an AQ in parentheses means aqueous. And aqueous means having been mixed with water or happening in water. And often when there's one aqueous, you might have more than one aqueous. Okay, so let's look at the difference between word equation and a written equation. So word equations are used to indicate products and reactants. This is where your products and reactants are in words, but everything else is in formula form. So like iron would be in a word, but the state would be in proper form. You have pluses and arrows. So the only thing here are your elements and compounds in words, versus a written equation is where everything is in word form. So solid iron and chlorine gas react to produce solid iron 3 chloride. That's written. Everything's in words. A word equation is where you have words and symbols mixed. Okay, so here are some really big important reminders. A big, major crazy mistakes that my students often make is forgetting their diatomic molecules. Now, remember, hydrogen gas becomes H2 and then a G. Nitrogen gas becomes N2G. Oxygen gas becomes O2G. Fluorine gas becomes F2G. Bromine gas becomes Br2G. Chlorine gas becomes Cl2G. And iodine gas becomes I2G. Now remember, these are just their standalone diatomics. So if you see things like hydrogen fluoride, remember, hydrogen fluoride's a balanced compound, so neither hydrogen nor fluoride in this instance would be considered diatomic. If you had iron 2 bromide, it's a compound. These are diatomics by themselves in gas format. Okay. So let's talk about the difference between skeleton, balanced, and unbalanced. So remember, we go from written to word, then you go from word to skeleton. And the skeleton equation gives more equation than the word equation. In your skeleton equation, you have your fully balanced compounds, all your chemical formulas, all of your solids, liquids, and gases in formula, your pluses and your arrows. The only thing that is not is balanced. So basically you have to have all your balanced compounds in your skeleton equation before you can go ahead and balance it in your balanced equation. Okay, so let's talk about the 4 steps to balancing. These aren't necessarily how to balance an equation, but they're like how the different steps go. So you have step 1, which is your written equation, which is all in words. You have your number 2, which is your word equation, which is your products and reactants are in words. Everything else is starting to look like a chemical reaction. Number 3 is your skeleton equation. It's unbalanced, but all of your compounds and everything else are balanced and in proper format. And then you have a balanced equation. So if you were given a written equation, you'd have to go through all these steps. If you were given a word equation, you would have to do steps 3 and 4. If you were given a skeleton equation, you'd just have to do steps 3 and 4. So it's sequential. And if you were given a balanced equation, you should be able to write a written equation from a balanced equation. Okay. So I want you guys to try independent practice now. I want you to try writing these. I'm giving you the word equation, and I just want you to go from word to skeleton. So I want you to go from word to skeleton for these 3 equations. I'll give you about 5 minutes. Okay, let's do the answers. So hydrogen becomes H2G, bromine gas becomes Br2G, and then hydrogen bromide becomes HBrG. If you do them each individually, that's how you would approach it. So carbon monoxide becomes COG, oxygen gas becomes O2G, and carbon dioxide becomes CO2G. I know they are not balanced. Remember, the whole thing doesn't need to be balanced, but each compound needs to be balanced before you can balance the equation. Potassium chlorate becomes KClO3G. Potassium chloride becomes KClS, and oxygen gas becomes O2G. Remember, if you're looking at these, question 1 is a mix between naming ionic compounds and naming covalent compounds. Hydrogen bromide is also hydrobromic acid. Carbon dioxide, oxygen gas, and carbon dioxide. This is all using your covalent bonding namings. And then question 3 is using your ionic bonding names. Right now, we're pulling everything from ionic bonding and naming from covalent bonding and naming and putting them into a compound, an equation to balance. And that is what we are doing at this point in time. Thank you.